Okay, let me give you a little background about how to simulate epidemics on networks. And I'm going to introduce two important concepts. One is the concept of social network. The other is the concept of agent-based model. Now, agent-based model models each individual in the population separately as a separate agent. It's computationally intensive, but in some way it's more realistic than a differential equation model, SIR model, SEIR model, because it does model individuals separately. So here are some examples of social networks. You can see that the boxes and circles, I think box and circle here indicates male or female, and these are the social connections between these males and females. All right, so these two interact strongly, these two interact strongly, etc. Here we have what's called a clique. All of the males, I assume they're males, all the males in this group interact with each other equally. Here's also a clique here. Here's a partial clique. But you can see these connections, and these connections indicate interaction. So you can imagine how this works with disease. If different people meet and talk together, then it's liable for them to transmit the disease to each other. Okay, so how does an epidemic spread on a network? Here's a very, very simple example. Here's a network of social connections. We have different people who interact with each other, and this person is infected on day one. So he could possibly infect those he's connected to, but he can't possibly infect in one day someone he's not connected to. These are one-day connections. So this person is connected to this person. The next day, this person might connect to this person. All right. So here it says everyone starts out susceptible. So here it says go around the infected person's contacts in turn, which would be 1, 2, 3, and 4. And here they say roll the dice if the number is 1 or 2, infect that person. So in this case, they're assuming there's a probability of 1/3 of infectious contact. And that's a very simple assumption. You could have different probabilities for different individuals. And you could also have these connections might possibly depend on the day. But the easiest way to model that is simply have different probabilities of different connections. All right? So it turns out this person, they rolled a 2, so this person became infected. Now here you can see there's no exposed time. You could easily modify this to introduce an exposed state. But this, we look at the first person, we went around all the neighbors, see who's going to be infected. Okay, so this person rolls a 6, this person rolls a 4, this person rolls a 1, gets infected. All right, so that person is infected. All right. Okay. All right, now here it says continue for all contacts, then the infected person recovers. In this case, they're supposing that the infection only lasts 1 day. If the infection lasts longer, the infected person would remain infected longer. Right, but here the infection only lasts 1 day, so there's no infection here, and this person can no longer be infected. They're assuming that this person is recovered, so he's uninfectable. All right, so now we do the same thing for each of the infected people. For this person, he only has 1 contact. This person has 2 contacts. So he'd roll the die a total of 3 times, right? So we start with that one. Okay, so that one doesn't get infected. There's nothing there. This person, now see this. So this person is no longer infected because his infection lasts 1 day. There really was no need to roll the dice for this person. That's inefficient coding, but that's what they did in this simulation. Roll the dice for this person. 6 doesn't get infected. This person gets infected. This person also gets infected. Right? So that person terminates and becomes recovered. So you do the same thing with this. Continue until the infection ends. Now we certainly want a more realistic picture of how the people in the community are connected. So we can do that by introducing institutions. So networks can model patterns of interactions of individuals within a population, and individuals we call individuals agents. Okay. So networks can give a more accurate picture of disease propagation than SIR models, where everyone is assumed to interact with everybody. We can construct an interpersonal network within a community by creating homes and institutions. All right, so here we have supermarket, workplace, primary school, and high school. So I have 4 types of institutions, and these blue dots are homes. Now these homes will include several individuals, several agents, and each agent will have connections, right? So if I have a primary school age child, he'll connect to a primary school, probably the nearest primary school. If I have an adult, I may have a connection to a supermarket or to a workplace. There are multiple individuals located at this family here. So if this, for instance, if this is an adult, they'll probably have a workplace, may go to the supermarket, may occasionally visit other supermarkets. Now, it doesn't mean that this person will visit all of those every day, but this person will have some connection to these different institutions. Okay, and then here I would have a high school age child in the same family connected to the high school. Now, of course, these people will be connected because they're in the same home. All right. Now, suppose I have someone in this family. This person may also go to the same supermarket. This may have another student who's also in high school. So you can see there are opportunities for this person to add contagion to this person. This person, the person here, could infect this person through the supermarket. So by building these institutions and by deciding who visits those institutions, we'll construct a network between individuals. Right? The idea is to eventually construct a network between individuals because, of course, institutions don't infect institutions. It's people who infect people. But what we have to do is we're going to have to specify institutions and visitors. So we're going to have to specify institutions and visitors, and we'll have to specify some parameters, like how often they visit, and when they visit, how infectious they are. I mean, if you're in a workplace, you may be working very close together, so infection is quite likely to be transmitted. In the supermarket, people may be farther apart, so infection is less common. Primary school, of course, kids are very close to each other. So that's a high probability of infection if the infection is not controlled in some way. All right? So that's what we're going to do. We're going to set up institutions, we're going to set up homes, and we're going to populate the model with agents, which are individuals, agents of different types, which will have different patterns of visiting different institutions. And then based on that, we will have a way of connecting agents with agents and essentially constructing a social network. More sophisticated than the social network that was shown in the previous presentation. Much more realistic, but the same idea. And we'll run it day to day, just the same way that previous simulation was run. Okay, so I think that's a fair outline of what's going on. And I'll give you more details in the next video.